I'm George Hammond, Chair of the Humanities Forum, which organized today's event. This is one of over 1,000 programs we started with the pandemic, where we bring authors in, we live stream them in. Today we have George Musser, the author of Putting Ourselves Back in the Equation, a very interesting book about physics and current quantum mechanic theories and everything, but where consciousness fits into this whole picture, and how, to some physicists' dismay, consciousness has to be part of it, and to other physicists' delight, consciousness has to be part of it. So you're in the middle as a science writer of putting that all together and finding everybody's different points of view, and I think you did a great job of showing all kinds of people's points of view on what's going on, and it also shows that there's not a consensus yet on this topic. So why don't we start, Joel, before we get started, if you're watching the live stream and you would like to ask a question directly of George, just put it in the chat room and we'll look at it a little bit later in the program. So one thing I found interesting that you mentioned in the book was that The Emperor's New Mind by Roger Penrose, the British physicist, was one of the things that really got you going. It happened to be a book that I read when it first came out a long time ago too, and I found fascinating as well. So why don't you tell a little bit about how that pulled you in?
Yeah, first of all, I'm delighted to be here and in a conversation with you. To me, that's the great intellectual benefit of writing a book, is I can finally close the circle. I can hear from people and the questions they have. Mm-hmm. So yeah, Emperor's New Mind, I actually first went to a series of lectures that Roger Penrose gave when I was in grad school. This was at Cornell, and it was a named, one of these named lecture series. I can't remember offhand. And 3 lectures, 3 days, really fascinating. Of course, I had to not do my homework, and it was a sacrifice to go to these events, especially as a first-year grad student, but it was just invigorating to do that. And then right after maybe the 3rd lecture that weekend, I went down to a bookstore and bought his book, and it's somewhere up on my shelf up here still to this day with my scribbled notes from that time. And it's just, first of all, just a remarkable intellectual achievement, as really all of Penrose's work is. He's pulled together physics, philosophy, speculations about the nature of the mind, and within physics, he's pulled together gravity, black holes, inflationary cosmology, quantum physics. And that alone, that kind of the synthesis of multiple fields is just so powerful, because I think that's a lot of the truth that we seek in the sciences, and scholarship more broadly comes from that kind of unification of different areas. The thing that the book is most noted for is really its commentary on consciousness and a possible relationship to physics. And there's a couple arguments he gives there. One is that consciousness, and it's an elaborate argument involving kind of Gödel's ideas and Turing's ideas, but essentially that consciousness cannot be explained by our usual laws of physics. Those usual laws are essentially mechanistic. Mm-hmm. And he argues that mechanistic processes cannot explain, first creativity and intuition, but by extension, our conscious experience. Second, the other thing is really remembered for is a possible connection to quantum collapse of the wave function. So really, one of the biggest questions and the open questions of physics today, it's been for a century, in fact, what goes on in the process of measurement. We can get into that later. Mm-hmm. But Penrose suggests that whatever it is, and he's got ideas, is connected to our consciousness, and in fact could account for our conscious experience. So consciousness, you can see how those two parts go together. Consciousness seeming to lack an explanation in our current framework of science. And here's a possible way to extend the framework, namely to include, for him, gravitational effects involved in the collapse of the wave function. Anyway, these are heady speculations. It may well be wrong. He's the first to admit in the book, and then in discussions I've had with him, he could be wrong. But really empowering just to see that kind of creativity and pulling together different areas. And I think that's really what science needs to get at some of these deep mysteries.
Now let's talk about the goal. You mentioned the goal right away in your book. But the goal of all of these disciplines is that we're all individuals, and we have this, what we think is a shared experience, and that most people agree must be a shared experience. There must be something objective about what we're doing. There are a few people who don't think that there is, but the majority, and that's the goal. How can we discuss with each other, especially outside of our own disciplines, the facts that make us feel that we are sharing an objective reality, and how can we get to understand it better? I mean, right now there's a sort of fad that there are no facts. And I don't mean here, in politics and everything. But we're going to pretend that that doesn't exist, and that we really are in this scientific endeavor, trying to get to this shared reality, and people come at it from all different disciplines, and they should all line up if we're close, right? They should line up, and we know that relativity theory and quantum mechanics don't quite line up, but they're close, that kind of thing. So, with that goal in mind, the idea of consciousness is a little bit like it disturbs some people because it seems not as objective. So why don't you talk about a little bit of why it disturbs? A lot of people want it to be deterministic, mechanistic, and then we're done. But
yeah. So you've touched on a lot of, in that one question that you've got so much packed in.
It wasn't a short one.
So there's an alignment or consilience among different disciplines of science and intellectual life, or rational thought, broadly conceived. Mm-hmm. And then there's the harmony we expect among our individual experiences due to they're all being rooted in an objective reality. So I think the assumption that I came into the book with, really coming from a physical science background, although I'm, of course, not only that, I have multiple interests, but mostly coming from the idea of physical science, and that probably most scientists would come to it, is that we have laws of nature, provisional laws, and they're always being developed. And those laws can be applied to the brain in some way and yield an understanding of our experience. So that would be kind of a scientific project of understanding the mind from the kind of the default way of doing that. So that takes the objective as kind of starts from the objective and attempts to recover the subjective. Now, I'm broadly on board with that program, by the way, but let me just point out an obvious issue with it, which is that epistemically, we start with the subjective and recover the objective. So we're all trapped in our own heads. We're all coming, and not in a pejorative way, but we're all coming and looking at the world from inside our own experience and attempting to reconstruct what could be accounting for that experience. And then we infer that there's an objective world out there. And you can go through arguments, as has been done really since Descartes onwards, that should be possible. And then you and I can go through this kind of process, and we can talk to one another, or any two people, any two intelligent agents can talk to each other and say, well, I see something. Hey, I see something too. And then there's a intersubjective agreement of that. And we try to build all of science on those kinds of agreements. And I think that's the process that is being interrogated now. And it seems like that should be the way to go, that we can eventually recover an objective reality from this. And those two sides of the world, the objective and the subjective, really should be equated in a sense. They shouldn't be sides of the world. They should be different ways of looking at the same world. But that's difficult to do. And it's issues in epistemology that have really been bracketed by the physical sciences ever since physical science became a thing under Descartes and Galileo, and really in that period. Although, of course, it has precursors going back to Democritus and so forth. So here's some of the issues. Here's an example of the issues that come up. We have theories of the objective, and how do we test them? How do we know? Well, we need to relate them back to experiments. So this is the empirical process. And the experiments are talking about experience. They're talking about our experience. So our experience and the way it's formed and the biases it can introduce, for example, or the filters we have, both because of we're finite creatures. We have certain senses. We have certain habits of thought. Those filters affect how the physical theory is manifest in our experience. And you can try to, and it has been productively punted on, bracketed for centuries, that, we don't really have to delve too much in our experience in order to make the connection from theory to experiment. But I think in some cases, you really do need to put that experience in. So this is the human element that I think has to come into our scientific theorizing. So it comes up in cosmology, for example. And there's a long argument here that one can give, but essentially certain theories, in fact, the leading theories of cosmology suggest that the universe we see is unrepresentative of the full totality of the cosmos, that we're seeing a fraction of the universe, essentially. Why do we see the fraction we do? Our own existence seems to be connected to that. We're seeing, for instance, just at the most basic level, a part of the universe that is habitable, because we could not, by definition, see a part of the universe that's uninhabitable. So we see a universe that's, of course, it's quite a violent and in some ways hostile place, but in relative terms, fairly habitable. Why do we see it that way? Well, we kind of have to. So the prediction of cosmology there has to be a filter added to the prediction to connect that theory of cosmology with the experimental findings that we have. So this is a long-winded way of saying that epistemology has to come into scientific practice. And this has been recognized, but I think it's becoming more and more an issue. And physicists have, by and large, historically not looked to the fields that are actually experts in that issue. Philosophy, neuroscience, which is fairly new as a discipline, but philosophy of mind before that, and other disciplines leading up to what's known as modern neuroscience. Physicists really need to knock on their doors and say, hey, I need some help here. I need some help connecting my theory of in this case of cosmology, to my empirical measurements. And I need your help in plugging in the human or other agent conducting the experiments.
So let's do something about what the popular image is versus the scientists. And I'll talk about the Big Bang for a second. So the Big Bang, we kind of, almost everybody agrees, almost all the evidence shows that there was a huge explosion somewhere between, there's a little argument about it, but it's getting closer and closer to 13.8 billion or whatever it is, so it's a certain amount of time, and it's a long period of time, but we make the assumption that it was in a vacuum, or that there was nothing there before the explosion. So we don't really know that, but that's the assumption. So in a vacuum, an explosion would be relatively spherical, right? Everything would go off spherically. And we know what we're seeing is a small light cone that's part of that Big Bang. So when people say the visible universe, the scientists know that's just a small light cone of a huge, much huger thing. But most people think, what we see is what there is. And it would be extremely odd, according to what we know about physics, for the only part of the Big Bang that happened was what we can see, this tiny light cone out of a sphere. There was one very interesting little piece of information in your book that said that microwave detectors have detected hydrogen gas 46 billion light years. That's the furthest edge. So you want to explain that? Where does 46 billion light years come to do with when we have a 13.8 and then there was nothing?
Yeah, so, there's a couple of things going on. So that's actually just a kind of a numerical factor that comes out of the expansion of space. Right. So we've got the 13, I just point out 13.8 is the current estimate, billion light years. We see events out to things that have happened 13.8 billion years ago. And what happened or may not or may have happened before then we'll put off on this side for the time being. And in those 13.8, it's actually a little bit less than 13.8 billion years, space has expanded a factor of 3. There's actually, you can look it up in tables, there's actually online calculators that will do it for you. So you kind of get the light travel time plus the space dilation effect. Result is that objects over that 13.8 billion years are now 46 billion light years apart from one another.
I see.
So
So
It is a source of confusion. And every time I wrote an article for Scientific American magazine on this, I'd have to put a little parentheses in. It's not 13.8 billion light years. It's 13.8 times a factor representing the expansion of space light years.
Right. Okay, great. So the hydrogen gas that's being noticed at 46 billion light years away is the hydrogen gas right at the beginning of the Big Bang. That's
right. So
yeah, it's not someplace else or some other location. It's
it's actually was here, literally here.
Right.
13.8 or 13.8 minus a few hundred thousand a few hundred thousand years ago, in every place that around.
It's the background radiation.
Exactly, it's the background radiation. But what is the background radiation? This often gets kind of put under the rug a little bit here.
Right.
Background radiation is showing us the distribution of hydrogen gas at that moment. Now, or I should say, the plasma that was congealing at that moment into hydrogen gas. And when it did, light no longer ricocheted around like a pinball in a pinball machine and was able to start. In other words, it wasn't bouncing among all the individual charged particles. It was able to start streaming more or less straight, and has been traveling more or less. Obviously, it depends a little bit,
right?
And there's lensing effects, but more or less in a straight line for 13.8 billion years. So when the light hits you, in a telescope, for example, or in one of these instruments, you're seeing it as it has gone for 13.8 billion years, and it's therefore revealing the distribution of that gas.
So another element of the popular versus the scientific. So people often say we're looking into the past when we look back. They could say the same thing if you saw rocks in the Sierra Mountains and say, you're looking into the past. What you really are doing, you're seeing something in the present, but you have scientific knowledge that can help you extrapolate what that means. So we see photons in the present. And know from our knowledge that it took 13.8 billion years to get here, right? So
and there's
actually look into the past, right?
Well, and what would it mean to look into the past? I need to think about that a little bit, but essentially you're right. You're getting artifacts and you're making sense of them,
right?
Be it the rock, and you're inferring from the geologic formations around you that we're actually on a highly dynamic Earth, and we're kind of seeing it as it froze in one moment in time because our own temporal window is so short. And some of those rocks may be billions of years, up to billions of years old. And likewise with the photons, you're seeing, and in some cases you're just seeing, and you being the scientist, so humanity, the representatives of humanity are seeing photons, a light in their telescopes, often just a few photons actually, you can count them on your hand, number of photons, and inferring through a long process what they must represent. And it isn't taken lightly, of course. There's a lot of convergence of different types of observations that are being made here. But it is pretty remarkable that people can look out and make these inferences about long ago events of things that no longer exist.
Yeah. It's also fascinating. You talk about how nature forces us to think about infinity and in nature. That's a concept which generally scientists aren't that happy about, but there's really no way to get around it. And I think it helps to think about an explosion going off in a spherical, everything going in a spherical, and that even though for 13.8 billion years you've got the diameter of the sphere is 27 point something billion light years for the sphere, and yet there's so many photons still with that kind of a diameter. That's a huge number. Yeah, certainly in the decillions at least, something like that, of photons. And so we are forced, as you said in the book, to face infinity. So why don't you talk? You talk about it in terms of neurons, and we'll use this as a segue over to the brain and neuroscience and artificial intelligence. So talk about that a little bit. Why we're facing.
Yeah. So just to riff off infinity a little bit. So we have a say mathematicians, mathematical physicists, have a interesting relationship with infinity. On the one hand, we might say, well, there can't be anything truly infinite in the world. Everything's ultimately finite.
Right.
But on the other hand, there are ways of understanding the world that seem to require the infinite. So if I draw a triangle, and I apply Pythagoras' theorem to that, and I infer that one of the sides is actually an irrational number. So that's in a way requiring a type of continuum, a type of infinity there. So infinity is always something we're using in physics and mathematics all the time. It may or may not be expressed literally in reality, but it's extremely important, and we couldn't live without it. So the physicist, friend to infinity, we use infinities. The textbooks are filled with them, we're using them all the time. And that's an important part of our analysis. Bring that same sensibility to the understanding of neural networks, as you point out. So one very productive way to make sense of a neural network, and let me just back up for a second. Neural networks of the sort of ChatGPT and image recognition networks and Google Translate and everything need to be made sense of, just as our own minds, brains need to be made sense of. These are deeply complicated systems that are extremely important, obviously, in our daily lives, becoming more so. And they're very perplexing. The mechanism of them is at a kind of the individual level. The neurons, kind of the what's a coder would put in the code, is fully understood. The psychology that comes from that is the difficulty. How do those, today billions of neurons interact, and how are they trained over time, and the dynamics that occur from that as well? How does that actually happen? And physicists think they can help. And they can help as just a first crack of it by saying, well, we've got billions of neurons. Let's say we've got infinitely many neurons. Okay, you might think that's kind of a step back. You took what's a problem, it was already hard enough when we had billions of them. Now you've gone all the way up. How are we possibly going to make sense of that? But infinity is special. It has a certain simplicity to it that, again, our methods of analysis, and I use the word analysis because of double entendre here, because actually it's a field of mathematical analysis that does exactly this, will allow us to gain traction, in this case, on neural networks. And that was something that started to be done, in the 90s, when neural networks as a concept went into one of these AI winters. It kind of fell out of favor for a decade or so. That work was left really in the journals to gather dust, and then was picked up again just in the past, say, 5 years, that you can think of these networks as infinitely big, and then that actually helps to simplify them. You can actually write an equation to tell you what the network will do. You can predict with certainty, or well, nothing's certain. You can predict broadly what it will do. And then you have to ask, well, they're not really infinitely big, so can we sort of back off from that assumption a little bit and say, well, they're very, very, very big? And you can actually do that. You can. This is a stage in the thinking. You start with the infinite network, and then you kind of ease off a little bit and have an extremely very large network. And there's ways to define that precisely mathematically. And then you can correct the initial infinite network solution for the fact it's actually not quite infinite, it's finite, and again produce an elaboration. And this is the kind of process that's now going on. It's fascinating work that's helping to make sense of these neural networks. Because if we can't make sense of them, we can't know what effect they're going to have in our society.
Mm-hmm. Using math and infinity, and as you said, it simplifies the way to deal with the problem. And it reminds me of maps. That you want to map something, because if you just have a copy of the Sierra Mountains, that doesn't give you as much information for dealing with the Sierra Mountains as a map does. Now, obviously, the map in this case has even less information in it, obviously, than reality. But when we're trying to describe this shared reality, we do this all the time. We're making approximations and everything. And I think it's important, for people who look at this from just a popular point of view and aren't scientists, to understand the process that it is mapping, it is leaving out information in order to try to get some kind of principles that we can then work with and then reapply and get closer. Because I think quantum mechanics is a little bit like that, and a few other things are a little bit like that, instead of being a description of the exact reality like the Sierra Mountains, it's a map of it, and that's why we can't quite, that may be, maybe not why, but it may be why we can't quite fit it with other things that we're mapping in a slightly different way, like with relativity theory. But anyway, that's just an analogy that I thought I'd throw in there, because you use infinity, but we know there's not an infinite number of neurons. There's no such thing as an infinite number, period, because the numbers are always specific. So there's infinite series, but there's not a number is, a certain number of neurons. Otherwise, they would be coming and going or growing. I mean, the number would have to keep increasing if it's infinite, because you could always add one, whatever. Whereas you think reality is a specific amount. So in any case, you had some graphs that you prepared to help understand these neural networks. And I think it's a fascinating way to go into the AI portion of what you're talking about, because obviously people are very interested in where that's gone in the last couple of years. Because
let me riff off
winter, and all of a sudden it's really big again. Right?
Yeah, exactly. We're back in the heat of summer. But let me riff off what you said about mapping, because I think those are really interesting insights. So, and this is relevant to neural networks and to science more broadly. So the map, we make essentially maps, simplified models or representations of the world all the time. This is what intelligence is. This is what it means to understand something. This is essential. This dimensional reduction, this kind of simplification of a very complex reality, is the nature of understanding. If we didn't simplify, if we just took a one-for-one representation of what the world was, we wouldn't have understood anything. We wouldn't have extracted any meaning from it. So the process, and this comes up in designing neural networks, for example, that you want them, the neural networks, to extract the essence of reality. You want them to get at it, right, rather than represent it in its entirety. And this is a huge problem with neural networks, because if not, I mean, there's a whole black art almost in the design of these and training of these systems, but often they are too literal. They'll take it in and they'll spit it right back out. Mm-hmm. And you don't want that. You want them to be able to generalize. And this is a question of how they generalize is really the place that physics has been helping the understanding of these neural networks. And before, I'm going to show you something about that in a second. I wanted to touch on one other thing, and that is, I don't think quantum mechanics on relativity should be thought of as maps. Mm-hmm. I think that's a slightly different issue. Okay. They're can be thought of as really what is going on. Of course, there are equations, and equations aren't really what's going on. They're representing something out there, but the something out there that's happening is actually going on. It's not a map. It's a literal truth according to the scientific process. Mm. And to create the complexity of the mountains or the seas or our own bodies, it's the repeated application of those laws over and over and over and over again in space and in time. And that's that physicist mindset, is that huge complexity of the world out there. We can get at it from simple rules. Yeah,
like Einstein's equation, E equals mc squared, is not a map. It's a fundamental principle of how things operate.
Exactly.
There's a difference. Yes, I agree.
Right. So and actually it usually isn't articulated this way in terms of maps and so forth, but we do talk in science, especially physics, a lot about a theory and a model. Mm-hmm. So you've got quantum field theory, for example, and the standard model of particle physics. The standard model of particle physics loosely can be thought of as the map of particles. Mm-hmm. You've got electrons, actually not protons, quarks, and the other particles. And that is the attempt to mirror what's happening in the world. That's sort of the map, you could say, an analogy to the map. And the theory, the literal workings of the system, or that's representing literal workings of the system, is the quantum field theory. Mm-hmm. So yeah, we kind of do try to tease apart in our scientific discourse the map from the theory and understand the mechanisms that are being created. But to pick up this issue of mapping, you wanted me to show a slide, so a slide I will show. So this is what is presented. So there's 3 boxes here representing, and as I discussed in the text, a temperature trend. So imagine you just look at the thermometer, and at every time, randomly through the day, you plot the temperature, and you imagine it's at midnight or maybe 2 a.m, it's the coldest, and then or actually just before sunrise would be coldest, right? So the temperature goes down at night roughly, and then rises maybe 2 o'clock in the afternoon, it reaches its peak, and then it cycles through the next day. So this is like a diurnal temperature chart. This is what the data are. Now, what does the network, indeed, what does our own brain do? So our brain is a neural network, but usually when I use the word neural network, I'll be referring to an artificial neural network. So if you give this data on the left frame to the neural network, what it is apt to do is something like this middle frame, what I'm calling overfitted. And it threads a curve through each and every one of those data points. And that's, in a sense, okay. If you wanted to know, kind of have a compendium of the measurements you made during the day, maybe that's so you want that. But if you want to know what's actually going on, namely that the sun is heating the ground or heating the earth, and you kind of create this roughly sinusoidal temperature variation over the day, something like you see on the right frame, that's kind of what our eye sees from the far left frame. You see something from the right frame. So you want the artificial neural network to do something like our brain does, pull out a simple pattern from complex data. And that's tricky. Neural networks, by and large, actually do better than they should. They sometimes do get too literal. And there's a problem, by the way, with being too literal, that if you go to here, for example, notice that the line goes through these points here, but in between them, it shoots down. That's basically, it's making an erroneous prediction for that time, and that's coming from this over fastidious attempt to fit the data. You want it to do something like this far right curve, and then you're going to get some error, but you've understood what's happening. The temperature is varying roughly sinusoidally based on the sun angle on the ground. And you're going to tolerate some additional scatter around that, and then maybe a higher order theory or an additional elaboration on that, what a weatherman would do, or what a meteorologist would do, would be say, well, it's due to the sun's under a cloud, behind a cloud here, or the wind is blowing off the lake here, or whatever. They try to pick out what's going on. But this is going back to what we were saying before about mapping, and that the map is, and the reduction of complexity occurs in mapping is good. It means we've understood. And based on this understanding of if you didn't know anything about the climate, you might, from a sinusoidal, roughly sinusoidal, it's not exact sinusoidal variation of temperature, be able to make inferences about how the climate works. And that's part of what we're trying to do with neural networks, is get them to that stage. Now, what's peculiar is that although they do sometimes fall into the habit of overfitting, more often than expected, they do get the right curve. They do extract out the answer. Let me just show that one thing to make one other point here. And that was, I said, well, we need to tolerate error. So suppose, I show you this last graph, and you said, well, look at how awful you are. You, in fact, you except for this one point here, you are over here maybe, you never got it right. You got 2 out of 50 right. You failed the test. But the thing is here, error is a sign of success. It is shown that you've tolerated these errors. You've actually shown a deeper understanding of how the world really works. And I think this is something we need to really take away in our own personal educations, that we should need to tolerate error. Error drives learning. If you don't error, you will not learn. If you get always 100 on your test, you're not learning. Or maybe more charitably, you're not challenging yourself enough. There's actually an interesting study, I don't know whether it generalizes to people, but certainly of networks, that 85% success is optimal. The system should be 85% right And if it's any more or less, then it's not learning at an optimal rate. So we all should be getting B pluses essential or B's on our tests. And if we are getting A's, we should take a harder test. And if we're getting C's, we take an easier test.
You're going to make a lot of high school students very happy. They're going to go back to their parents with that one and say, hey, see, I'm doing perfectly according to George Musser.
And it's actually, it's interesting when I've spent a lot of time talking to scientists. It's one of the joys of my job. How many of them actually really struggled in school? Mm-hmm. So there's something else you can tell your parents. Einstein actually did quite well in algebra. That's kind of a myth of that. But some of the leaders of quantum physics really struggled with the topic. A leader of quantum field theory that I spent a lot of time interviewing took the class 3 times. Mm-hmm. So, in a sense, and became an expert in that very field. Mm-hmm. So, we need to tolerate our own mistakes and that of other people.
Mm-hmm. Yeah, well, it's interesting. Again, we were talking about maps because that well-fitted thing is like a map, and maybe it's giving us the information, which is if you erase all of the other variables, this is what the sun is doing on a daily basis. It causes this kind of a curve, and then it's adjusted because of as you said, the wind, the clouds, all the other things that shifted around. Rains, it goes down, et cetera, et cetera. So you just kind of have to know what it is that you've eliminated all the other variables. You have to know what it is that you're looking for in order to see whether that makes sense, So,
and it's not obvious. This is why this is
right.
Science is a creative process, and you have to try a lot of things. They don't work. You kind of have to feel your way through. Often you come up with an idea, and this is historically true, erroneously. And the error leads you to the truth, and then you kind of kick away the error that got you there, and you just cling on to the truth that you've extracted from that. But it's difficult, and the networks have a problem with it too. We make mistakes. It's actually remarkable how few mistakes our visual systems make, considering that they're doing exactly this fitting process, 10 times a second, 100, whatever times a second. We are always inferring what's going on in the world and from the evidence that our eyes and other senses collect.
Well, fluid dynamics has still got people, looking for that fit, right? For what would be a well-fitted thing of what's going on here. It's so complex.
And actually, it's actually funny you bring that up. That was some of my thesis work was on fluid mechanics, and I've always been fascinated by it. It was a class I struggled with in college, and I struggled. The struggle represented that I was so engaged by it. One of the people I talk about in my book actually got his start in robotics and in neuroscience as a plumber, essentially. He was fascinated. He struggled in school, ended up as a piping engineer, essentially a plumber. This was in Japan, and just wanted to understand fluid flow, specifically banging pipes like you get in your radiators when they come up. And it led him to really become a leader in thinking about robotic versions of our brains.
All right, so now all this neural networks are being used in order to try to accomplish artificial intelligence. And why don't you talk a little bit about that? That's again, like a big push. Everybody knows about it. Everybody thinks, I don't have to write an essay anymore because ChatGPT is going to be able to do it for me, that kind of thing. But why don't you talk a little bit about how these complex neural networks, with the modeling even in infinite number of neurons, is moving towards better AI than we had before.
Yeah, so what's a good way to approach this? First is that the current wave of interest in neural networks was driven by engineers, was driven by technologists, coders. And that's actually what kind of makes neural networks fun, is you can code them up pretty quickly. There's subtleties, of course, and complexities, but they're essentially quite simple things that, when combined in the right way and given the right kind of a data set, create huge complexity. So the current wave is really driven by people trying different architectures of neural networks, different data sets. The data sets, actually, I keep coming back to that because it's been a huge part of what made the neural network revolution happen, is the availability of data from the internet in a way that hadn't been really available before. Then you ask yourself, how do the things work? And I think we have reached it. We certainly are reaching it. The difficulties that engineers have in designing better networks, fixing the flaws or plugging the gaps in their current networks, that society has in deciding the impacts of these networks come from just the puzzle of how they work, how they create something that seems so human-like, how they're intelligent, to the extent to which they are human-like. I mean, not very in some ways, quite human in other ways, and people debate that. This is, I think, where theoretical science, physics in particular, helps. It helps to break open the black box, because that's what physicists do in multiple ways. I mentioned the infinite assumptions that we make. That is an infinite number of degrees of freedom in a system, and that helps us to simplify it. But just imagine all the other successes physics has had. How does it describe the air in the room? Which is an incredibly, ridiculously complicated system of just 10 to the 20, I don't know, in this room, 10 to the 24, 25 molecules, for example. It has a series of methods and approximations that allow it to do that, even though the individual molecules behave fairly simply, at least in the assumptions that are made here. You can work up to why pressure varies the way it does, volume, and the other so-called thermodynamic variables, the kind of high-level variables. So this is all related, but another thing that physics does is navigate scale. This is something that comes up all the time in understanding particles, because particles agglomerate to form composite particles, which agglomerate to form composite particles. So protons are made of quarks and gluons. Protons in turn form nuclei, atoms, molecules, and so forth. And we have a method called renormalization. There's a reason it's called that, is not important here. That is a way to, it's like having a zoom die. You can kind of turn the die and zoom in and out on your system to look at, okay, we'll look at the particles. Now we'll look at the composite particles. Oops, we'll go deeper. We'll look at the fields, and we can go in and out. And there's a principled way to do that. And those methods and others can also be applied to neural networks. They can be applied to actually a lot of things, and I discuss some other applications in the book, just understanding the concepts of causation. For example, one can apply these methods.
All right. So we actually have a question about AI that came in from the audience. What concerns you about AI? Do you agree with some advocates who want a regulatory body or organization to oversee AI technology?
Yeah, so I'll put two hats on for this. One is that in the book, I don't really get into this that much. I've been to conferences, and these discussions about AI, bias, safety, risk come up, with great regularity. And I don't have a professional opinion on it, but I will say that, so I'll speak more as a member of the public on this particular topic. And I would say I'm most concerned by misuse of the systems. I'm less worried, at least in the near term, about wiping out humanity, those kinds of existential risks. Maybe they're an issue, but they're certainly not an issue at the moment. We have other ways to wipe ourselves out.
Yeah, so we're good at that anyway.
So, and dumb machines, non-AI machines are unfortunately quite capable of that. But okay, an issue that should be dealt with. But the immediate concern is really things like misinformation. It's the, more broadly, I would put it, the uncritical use of the output of these networks. So, and maybe this is where my book actually does help out, because to the extent the relevant chapters in the book will help you understand, or help the reader understand networks, their limitations, their workings, you can then take that knowledge into your own use of the networks. And in addition to other books and other resources that you might have on this, I think everyone should actually just try playing with the network. There are tools online that you can do, that you can kind of like little applets you can use to see how networks work. You can actually just use ChatGPT and see the kinds of foibles it has. and draw your own conclusions about how reliable that is. But my own sense is that it's the uncritical use, especially in mission critical situations. So taking there's that famous case of a lawyer writing a brief. ChatGPT. I don't know how common that really is. I think most lawyers are much more sensible. That plus they want the billable hours.
Yeah, I was going to say that didn't seem to match my reality as a lawyer at all.
Yeah, my mom's a lawyer, so I can't be too cynical about lawyers. So but one should never do that. I mean, the ChatGPT is incredibly powerful, but it's only a tool, and you have to learn through experience how best to use that tool.
Yeah. So your basic approach is that, like most scientific advances, it can be abused, misused, or it can be used well. It depends on the people and what they do with it more than the technique itself.
Yeah, that would be the way. But I think maybe just to drill a little bit down, my plea to people is just try using the systems and learn from them. I mean, I've talked to a lot of these scientists, as I said, in the various places, and just through brute force experience, they've kind of reached their own conclusions about the systems. And that's, I mean, the systems have a psychology to them. They not human psychology, but it's related because they're trained on human data and they're modeled roughly on us. But they're not, it's more subtle. It's not something that can be easily summarized, but one has to just try doing it. And then the concerns, and maybe the listener was alluding to those, there are obviously larger concerns that are even larger than misinformation, manipulating us or people using it to manipulate other people. And then that can scale up. What about if it's used in a drone? And then the pace, the drones are attacking other AI drones, and then there's like an arms race that develops and we lose control. Yeah, those are all issues. But the thing we definitely unequivocally face today is people misusing those systems.
Mm-hmm. So in a way, you're saying that there are patterns, a little bit like people who try to see what the patterns are in standardized tests and then get better at them, that kind of thing?
Yes.
Okay. So here we have another question, a big, broad question for you as a science writer. Some of us have family, friends, or coworkers that don't believe or trust science. As someone who writes for scientific publications, how do you suggest we have civil conversations about science and their, its role in human society, that kind of thing?
I just finished reading a book on this very question.
Yeah. Oh, good.
E. McIntyre. I literally finished it last night. So I recommend the book, How to Talk to a Science Denier. Mm-hmm. And I'm not getting paid by him for that book, by the way. It's each of us has to kind of thread that needle for ourselves. The kind of bottom line of this book is a respectful conversation, the not condemning someone, trying to really have a genuine dialogue. Often the dialogue will proceed not on the case at hand, not on the actual facts about climate or whatever, but on shared values, on try to find some commonality with people. It's a lot of work, by the way, and it may not succeed. You may not, for all your effort to find common ground and all the beers and coffees you share with that person and the Thanksgiving dinners, may not bring them around, but it's probably going to work better than you idiot, kind of those kinds of insults. There has to be, a sense of wanting to get at what's going on. I think, cynical as I sometimes can be about humans, I think most people, 99 or whatever percent of people, those who certainly don't have vested interests in certain outcomes, want to get it right. I don't think anyone wants to be wrong. Right. I think they just kind of have lost the path, and you, with some gentle encouragement, can pull them back on the path. So in the editorial position I had before going to Scientific American, I was at this very small magazine, actually based in San Francisco. I used to live out in the Mission District. I loved it. I would get a lot of strange letters. Crazy. Let's call them crazy, right? And I really tried to be sympathetic to them. I mean, they were saying things like, first of all, they insult me personally for adhering to Einstein or whatever. So I tried to look past that. And I think the thing I would take away is those people cared. They cared about the world and the way the world works. They may not have been right according to the scientific viewpoint or just a rational way of thinking, but they had the essence there. They cared. And I tried to the extent I could to work with them. And also, here's one positive thing that did happen with that. Maybe the listener could take this away. When I responded, they were like, oh, wait, you listened to me. That's literally, I would get that over and over. You responded to me, and I'm sorry I came across in an insulting way in my original communication to you. So often it would develop, once you made that initial swallowing of your pride and just try to engage with them respectfully, often there would be reciprocation.
So I think one thing which you kind of touched on there with their caring is it's useful to remember that they're probably just as frustrated that you're not adjusting to their thinking as you are to theirs. And so, I mean, it's not necessary for everybody to agree at all. And what makes good science is for people to be arguing about things, but doing it rationally so that people can listen, you know. But not everybody's trained to listen to rational argumentation, you know, and get it, because they that's not their background. There's a lot of professions that's required, but there's a lot of professions it's not. So
Great. And you have to make your own assessment as to what this is worth to you. I mean, is that an important friend? Is that an important partner in your life? Or is it just, you know, there's really no point in trying to convince them, so maybe just drop it. I will say that the times I've really worked to try to understand and convince people, I've really learned. So I did a big project at Scientific American, this would have been the early 2000s, on climate. And I did a whole series of blog posts. This is actually around the time we started our blog. And I had invited people to write in, and I tried to listen to them why they didn't accept, or why they didn't agree that the average temperature of the Earth is rising due to human activity, anthropogenic climate change. Why they didn't accept that? And in the process of working through their critiques, I don't know how many of them I convinced, by the way, but it certainly helped me, because in the process of working through what they said, I learned a lot. I did a lot of reading on what known as fingerprints, climate fingerprints, which is kind of the more granular use of climate data to individuate the different possible causes of climate change. If it's due to solar increase, suppose the sun were getting hotter, and you imagine that would be the reason that Earth is warming, then you would expect a certain pattern. Both the stratosphere and the troposphere would be getting warmer. You'd be getting warmer uniformly over the oceans, the continents. And it turns out that you don't see that kind of uniform heating of the surface. You see differences among these different areas, both in altitude and laterally across the surface. So you can go through that kind of fingerprinting process. It was big in the early IPCC reports. And I learned a lot from that engagement that I had. So that's a reason to engage people, I think.
yeah, I mean the old scientific end. You know, if you go back to ancient Greece, the whole point was to ask a whole bunch of questions and to get all involved in trying to answer them. And usually, if the questions are, as you say, caring, sincere, and somewhat informed, they often give you at least another angle for yourself on getting a better idea to go forward and get an even better idea what our shared histories or what our shared space is really like, because those people are also experiencing it. They just experience it quite differently, you know. Or
there was another study that was regarding healthcare. This would have been made around the time of Obamacare. People obviously, and to this day, have huge disagreements on this. But I think the author of the study said, try this. You're having this discussion at Thanksgiving or, you know, maybe your next holiday event, and you get in a big healthcare comes up or some argument comes up. Just take a step back and ask a more kind of procedural question. How does health insurance work? Forget whether it should be national insurance or private insurance or whatever. How does it work? And I guarantee you almost nobody knows. So you will learn something from that. And they'll probably say, well, I don't have any idea how it works. I send my bill in and it comes, you know, whatever. Yeah. So you can kind of pull back sometimes and try to engage on what are really the non-controversial aspects of a problem and which are often extremely difficult parts of the problem. How does the climate system work? I mean, that's a big question. You'd have to break it down, but you can sort of get at climate. That'd be another avenue with the climate denier is saying, well, tell me a bit about general circulation models. I mean, whatever.
Yeah. Well, it's interesting, too, when to go back to the medical insurance for just a second. The history, why did it get started? Well, there were wage controls during World War II, and so companies wanted to offer something that wasn't part of their salary, but so that's where fringe benefits started from, and the doctors liked it right away because it guaranteed that they were going to get paid, because before half the people didn't pay their doctor bills, and from there we went in 75, 80 years to here. It's.
Yeah, and Germany had a very different trajectory coming out of German unification.
Right.
NHS in the UK, again, there's very particulars for all these systems.
Yeah. So we have another one here, which is a big question about consciousness and neural networks. Will non-organic machines become capable of experiencing subjective conscious experience like pleasure, pain, love, longing, etc., or is it just an imitation of what we do?
Yeah. So this is big question. I've written not just in this book, but in other pieces about this, and we'll continue to write. In fact, I'm working on an article for Scientific American on this issue. So I think let's take the word will. Will they? Or maybe replace the word can for the time being. Maybe in other words, dissect the question. Yeah. Can neural networks, can AI more broadly become conscious? And I think the answer is yes, they can. So then the question is, what type of neural network or what type of AI system, construed more broadly, would be required to do that? So you can imagine a range of possibilities. If you did a kind of one-for-one duplicate of our brain in what's known as a neuromorphic computer, so one that's not based on the same logic gates that a conventional computer would be based on, but is designed really to mimic the brain per se. And if you actually kind of built almost like a model or a identical model of the brain in that neuromorphic circuitry, would it be conscious? I think probably most people would say yes. Even people who deny machine consciousness in other realms would say if you really tried to duplicate the brain in an artificial system, yes, it would be conscious. But so then you can kind of move off again and ask whether our current hardware, our current neural networks, our GPT-4, maybe GPT-5 or Lambda or one of these other models can become conscious. And that's tricky. So that's one of the benefits, I think, of theorizing about consciousness. Benefit number one is it's so interesting, it's so puzzling, I want to know how my own brain works. But the practical side, if you can call it that, is you can then apply those theories of consciousness to actual systems in the world and say, is it conscious? Is it conscious? Is this third one conscious? Mm-hmm. So for GPT, I think the analysis was done for, say, GPT 3.5 or maybe the general architecture of GPTs, these transformer networks, so-called. David Chalmers went through this exercise just about a year ago now. I think it was maybe exactly a year ago today or a year ago yesterday, and went and applied various theories of consciousness to transformer systems and said probably not. They're probably not conscious. They lack the features that the various theories say are essential to consciousness. I mean, whatever theory, and you'll disagree on what those theories are and what features, but they seem to lack them all. Right. And David Chalmers is a very careful philosopher, and he wasn't equivocally said, he kind of said maybe there's a slight chance or there's a probability that they're conscious. He didn't want to rule it out altogether. But he left open in that same paper, which he then delivered. I went to a conference that he went to in, I guess, February, and he kind of updated the paper for that, and he's probably updated it since then. Would ask what would have to be added to a GPT-4, let's say, to make it maybe more probable that it's conscious. So there's things like some theories, and maybe I can show a slide in a second, but some theories ask that there be basically feedback loops. Mm-hmm. What's called recurrent processing in the systems. And what that does essentially is it gives the system an internal dynamic that if it were just going from input to output one way, would lack. If it starts to loop around, it starts to develop its own internal dynamics. That's kind of what we have in our own heads, and might be qualified as being conscious. And the systems such as GPT don't have real recurrence. They have something close to it, and that's kind of why they've been able to scale up, is they had just enough something like recurrence. But recurrent networks are more demanding to train, so they kind of backed off from that a little bit, and they made something that was just a one-way system, not looping back, but was almost captured some of the qualities of recurrence, the kind of memory effect that a recurrence would have. So if you added true recurrence to the network, there would be, according to those theories, there'd be conscious systems. And you can do that exercise for the other systems. And what I'm looking at now for this upcoming article is the global neuronal workspace, or global workspace theory. There's another theory of consciousness. I'll actually get into it in the book. So it's been fun exploring this other new and very interesting and highly plausible theory that puts consciousness in the kind of interaction among the modules in a network. So our own brain has multiple modules, like the motor system, the visual system, auditory, et cetera, memory, and all those modules have to interact. And the workspace, so-called, is the place of that interaction. And it's limited by design. It's meant to be kind of a funnel through things have to go through. And that funnel concentrates our thinking on a topic and helps us develop understanding. So there's a real rationale to put that into a machine system. It would help the machine gain understanding in a way that GPT doesn't seem to, or at least broadly doesn't seem to have. It actually has narrow areas of understanding, but generally doesn't really understand what it's doing. So adding the workspace might achieve that. And if you did that, and people are trying to do it, the machine may be conscious. So I think, can we build conscious machines? Yes. Will we? Quite probably, because again, I think there's a reason. I think there's a reason we're conscious in the evolutionary terms, and machines will have that same requirement. And then you have to. Then there's obviously moral questions that come out of that. If you build a conscious machine, can it suffer?
Yeah.
Can it have pain? Its consciousness and its experience will, of course, be quite different from ours. Maybe the category pain won't apply to it. One hopes, by the way, that will be the case. We shouldn't be building machines and then essentially torturing them. Mm-hmm. But definitely, if you go down this road, you better start asking that kind of question.
Yeah, that detail goes right into one of the big ideas that you mentioned, that most physicists think that consciousness, or most scientists think that consciousness is an emergent property. That's a kind of concept that's maybe a couple decades old now, but is highly popular as a way of explaining where consciousness comes from. So do you want to explain what an emergent property is a little bit to people? Because I think a lot of people have heard that are interested in, for example, your book. But the idea is a little bit vague.
Yeah, well, and it's definitely vague. And
yeah.
I have a whole chapter that tries to dissect emergence as a concept, because it usually is used in a hand-wavy way. So you have property, let's take consciousness, of a brain, my brain, let's say, any human brain, or mammal brain, and you know that the individual ingredients probably are not conscious. And that's an assumption, by the way, that we can revisit. And a lot of people, the panpsychists, for example, do. But let's assume for now that the atoms, maybe even the neurons, or maybe clusters of neurons, they're not conscious. But the high-level system is. Mm-hmm. So something happens. And we call that something that's happening emergence. So some group dynamic is a way to think of emergence, some collective property of those inanimate or unconscious ingredients produces at the high level consciousness. Now, emergence, I never made this comparison before, so you're the first to hear it and the first to pop in my own way. Emergence is kind of like dark matter. Mm-hmm. It's one of these words science puts up and invents as basically a stand-in for ignorance. So we don't know what's holding the galaxy together, and it should, if our observations are right, be flying apart. So we say, there must be dark matter. Mm-hmm. We don't know how base level connects to high level emergence.
Right.
Now, I'm being a little unfair. There are ways to understand dark matter, certainly. I mean, it's definitely more than a stand-in for ignorance at this point.
Right.
People can pick it apart a little bit, but that's the original use of the term was basically, heck, if I know what's holding the galaxy together, we'll call it dark matter. Dark matter. And now we've been able to develop. So science works like this. We know it has to stair step up. Let's move. We call this thing dark matter. Let's see if we can characterize it, or maybe way. Same thing with emergence. We know that there's group dynamics that occur in nature, that things, and not just consciousness, all sorts of things. Water, made of H2O molecules, right? But has collective properties. I can pour it, it has liquid properties, but actually an individual molecule doesn't have. I can compress it, or I can freeze it, I can boil it. Again, these are all collective properties. The state of matter that it's in is a collective property, an emergent property. Pressure, volume, maybe volume, I don't know. Pressure, certainly. Temperature, definitely temperature is an emergent property of multiple molecules, multiple degrees of freedom of a system.
Right.
And consciousness may be that. The question is, how does it emerge? Okay, that's the next thing you need to ask. Okay, if someone says, I think consciousness is an emergent property. And you say, oh, well and good. How? So in chapter, whatever my chapter was on this, 6 or 7, I actually do talk about some ways emergence can happen. And in one way or another, that boil down to the assembly of structures within. So if you take the atoms fit together in a certain way that creates a structure, and the structure has some meaningful dynamic as a structure, as opposed to just of the components that are in it. And then that can be assembled. So an atom would assemble into an hydrogen and oxygen into an H2O. And H2O, by virtue of the way charge is distributed in it, for example, has properties by virtue of being H2O, as opposed to being just a bunch of hydrogen, just a bunch of oxygen. And then you can bootstrap up in that way. But yes, my default assumption is that consciousness is emergent in some way in the brain, and all the theories that I deduce in the book are ways to understand that. I did bracket earlier, and I said there's a group of people who don't think that's true, and they do think consciousness is wired into the base level of reality, those panpsychists, and there's variants, dualists also. And there's arguments you can give for that. The irony, though, is that they, too, the panpsychists, also have a need to explain emergence. Emergence is always going to be there as an issue. So in their case, consciousness doesn't emerge from unconscious ingredients, but high-level consciousness emerges from low-level conscious ingredients. So there's still a connection problem, kind of a scale navigation problem or collective action problem that needs to be solved there.
Well, we've run out of time, but George, is really a great discussion, and we've just dipped into the book a little bit. There's lots and lots of ideas in it. I have this fantasy that maybe 2,000, 10,000 years from now, there will be a shared reality that we can describe objectively, and people will say, how did this shared reality get described accurately? So, well, it emerged from all of those discussions. The shared reality description is going to be an emergent property as well. So let's hope that this helps towards that.
I hope so.
Well, thank you very much for joining us, and good luck with the sale of the book and putting yourselves in the equation, taking consciousness, put it into the physics by a great science writer, George Musser. And so ends another event at the Commonwealth Club in its 121st year of enlightened discussion. Thanks a lot for joining us, George.